Good morning, class. We are looking at Chapter 2, Limits, Section 2.5, Continuity. We've covered limits of sequences, limits of functions at infinity, limits of functions at finite numbers, limits, algebraic methods, and now continuity. The synopsis of what we covered: limits of functions at finite numbers, finding limits by numerical and graphical methods. And this definition, we read the limit of f of x as x approaches a equals L. The limit of a sub n as n approaches infinity equals L. We say that a sub n converges to L. Limit of a sub n as n approaches infinity is infinity or negative infinity or does not exist. We say the sequence diverges. And to find the limit, simply plug in the value and observe. We are interested in finding the limit of f of x as x approaches a in all these three cases. Notice we are approaching a from the left and right, which means we are moving this way from the left of a, this way from the right of a, this way along the y-axis, from the bottom and the top. In all three cases, the functional value is not interest at this point. The limit is, and the limit is L. What's the difference? The functional value, which means exactly at A, is also L here. The functional value at A is something else, B here. And the functional value at this point is not given for this case. Therefore, we write part A, f of A is L. Part B, f of A equals B, which is not equal to L. Part C, f of A is not defined, but in each case, regardless of what happens at A, the limit of f of x as x approaches A is given, and it's equal to L. However, in these two cases, the function is not continuous at x equals A. Horizontal asymptote of the curve y equals f of x has the equation y equals f. If the limit of f of x as x approaches negative infinity is L, or limit of f of x as x approaches infinity is L. VA, short for vertical asymptote, has the equation x equals A if the limit of f of x as x approaches A, or A from the left, or A from the right is either positive or negative infinity. Limit exists if one-sided limits are identical. A function has a limit at A if the limit of f of x as x approaches A from the left equals L, and the limit of f of x as x approaches A from the right equals L, which result in limit of f of x as x approaches A to be L. So that's the synopsis of what we covered. And now, section 2.5, definition of a continuity. A function f is continuous at x equals A if the limit of f of x as x approaches A equals f of A. What does it mean? Number one, f of x exists. That means the output at A exists. When we say the output, we mean the y coordinate, okay? The limit of f of x as x approaches A equals L exists. The limit as x approaches A exists. And finally, the two are equal. The limit of f of x as x approaches A equals f of A. The limit is the same as the output, the y coordinate of the function at x equals A. A function is continuous over an interval I if it is continuous at each point A in that interval I. If f is not continuous at x equals A, we say that f is discontinuous or has discontinuity at x equals. We are all familiar with direct substitution property, a continuous function. At a has the following limit value, the limit of f of x as x approaches a equals f of a. Functions with the direct substitution property are called continuous at a. Every function we studied in pre-calculus, in college algebra, they are all continuous in their entire domain, which means we should know what the domain of those functions are. Example 1, at which number is f of x discontinuous and why? We are looking at this function, everybody. And so, with that being the case, we notice there's a discontinuity at 1, 3, 5. Why is that? Let's discuss the reason behind each case. By the way, this is the definition of a continuity and the definition of a limit where one-sided limits are equal. So let's look at number 1. So when we look at number 1, as far as the limit, we are going to approach 1 from the left and right. And as far as the functional value is concerned, we look for a solid point. There is no solid point, so f of 1 is not defined. And that's the end of the story. It makes it discontinuous. However, just for the sake of argument, what is the limit? As we approach 1 from the left and right here, here's the left going this way, right going this way, we go up and down, and the answer is the y coordinate here. For this point, the y coordinate is 1. So the limit of f of x as x approaches 1 is 1, but the reason it's not continuous because f of 1 is not defined. The next number is 3. What's the problem here? The limit of f of x as x approaches 3 does not exist. So we need to see the reason for that. So that's why for number 3, we look at the left and right. The limit of f of x as x approaches 3 from the left, and the limit of f of x as x approaches 3 from the right. So from the left, we are moving this way. We are here. And the answer is -1. So this is -1. From the right, we are moving this way. That means in this branch. So we are looking at this point, and the y coordinate is 2. So the limit of f of x as x approaches 3 from the left is -1. The limit of f of x as x approaches 3 from the right is 2. Since they are not the same, the limit does not exist. Also, for information, what is f of 3? You look at 3 and look for a solid point. Here's the solid point. What is the y coordinate? -1. And by the way, we notice these two are the same. The function is not continuous, but we say it's continuous at 3 from the left. Again, It's not continuous at a equals 3. But the terminology is that it is continuous at 3 from the left because we have a solid pointer. And the last number is 5. Let's look at number 5. So what's going on? The limit of f of x as x approaches 5 is not equal to f of 5. Why is that? Well, let's approach 5 from the left and right, which means we are moving this way and that way. From the left, from the right, and in both cases, we are moving towards this hole as a y coordinate of 1. So this limit equals 1. What about f of 5? You look for a solid point. F of 5 equals 3. So they are different. It fails to be continuous at this point. So to recap, it's discontinuous at 1 because we don't have f of 1. F of 1 is not defined. It fails to be continuous at number 3 because we have different limits. The one-sided limits are not the same. The limit doesn't exist. At 5, the limit does exist. The functional value exists, but they are not identical. The limit of f of x as x approaches 5 and f of 5 are different. Example 2, g of x is 1/2 x plus 3 for x less than -2 and x minus 1 for x larger than or equal to -2. This is the piecewise defined function. Again, definition of a continuity on one-sided. Is g of x continuous at x equals -2, y or y not? Again, as I mentioned, this is a piecewise defined function. And if we look at the top piece, that's the line. Let's call it y. It's y equals 1/2 x plus 3. And if you look at the bottom piece, that's the line y equals x minus 1. So we have two half lines in essence. Each function is a line, and each one is continuous from negative to positive infinity. Because this is defined all the way to -2. So this is continuous from negative infinity to -2. Because this is defined after -2, it's continuous from -2 to infinity. And anytime you have a piecewise defined function, you have to look at the end point where they meet. This point is of question. We don't know what's going on with that point. We have to check it. But every other point is fine. That's why we are looking at the end. So there are three things we want to consider. Number one, we want to look at the functional value. To look at the functional value, you look for the equality sign. Equality sign belongs here, and therefore you go with the bottom function, the second piece. To evaluate the function at -2, you put it in there. And you're going to write g of -2 is x minus 1 such that x equals -2. This is the notation when you don't have a specific function. So to tell your reader that you're evaluating the function. So this line segment is read such that. So you plug in, and you end up with -3. Now you look at the limit, so you look at the left and right. So we start with one side, for example, the left. And to do so, you go with the less than and you pick the top piece. So the limit of g of x as x approaches -2 from the left equals this 1/2 x plus 3 such that x is equal to -2. You plug in. This gives you -1 plus 3 gives you 2. Now you look at the same thing from the right. And this time, the right side limit, you need to look at greater than. You look at the second piece, x minus 1, and you plug in. So the limit of g of x as x approaches -2 from the right is x minus 1 evaluated at x equals -2. You plug in, and you get -3. The left side limit is 2. The right side limit is -3. That makes it such that the limit does not exist. Since the limit of g of x as x approaches -2 from the left is not equal to the limit of g of x as x approaches -2 from the right, therefore, the limit of g of x as x approaches -2 does not exist. And therefore, the function is not continuous at x equals -2. G of x is continuous at x equals -2 from the right. Well, notice the functional value and the right side limit, they have the same value. The answer is yes. So I hope everybody is clear as to why this is the case. Example 3, types of discontinuities. This is a line with a hole. That's the same line with a hole and a solid point. A rational function, when you graph it, you're supposed to put it in its lowest term. So whenever there is a common factor between the top and the bottom, it creates a hole. So ultimately, there must be a common factor between the two. And in this case, at 2, we have no idea what the answer is. It's not given. But at this point, at 2, the answer is 1. It's given. Parts A and C, known as removable discontinuities. We could remove the discontinuity by redefining f of x at just the single number 2. So in both cases, we can easily fix it. But to understand how to fix it and how to redefine it, let's go back to this one and factor the numerator. The denominator has the factor of x minus 2. So the numerator has the same factor. X minus 2 drops and it becomes x plus 1. And f of x becomes x plus 1 such that x not equal to 2. Now this function, without this restriction, is a continuous function. This function is just a line. This function is the same line, everybody. But no restrictions. Same line, no restrictions. So x can't be 2. if you put it in here, the whole would have the coordinates 2, comma, 3. So you can find the precise location that you have to put a hole. So if you want to graph this, you graph this line and you put the hole there. You want to graph this, you graph the same line, you put a hole there, and since they said this one, it means the pair 2, comma 1. The meaning of this is the pair 2, comma. But as I mentioned, it's just 1 point. If you redefine the functional value at 2 to be this number, so if you change this to number 3, it fixes the problem. That's why it's called the removable. However, if you look at this case, f of x is 1 over x squared if x is not equal to 0, and 1 if x is 0, it gives you this point. There's nothing we can do. We have a infinite discontinuity, or VA, or vertical asymptote. This one is called the greatest integer function. You have jumps. So this can't be fixed. Infinite discontinuity or vertical asymptote, this can't be fixed. Jump discontinuity. Is h of x continuous at x equals 3, and h of x is defined as x squared minus 9 over x minus 3 for x not equal to 3, and 7 for x equals 3. So because this is the case, that means the function is always that, except at 3. And remember, when you want to take a limit, you take this function and you take a limit. And before we continue, I want to make sure we understand the meaning of this is the pair 3, comma 7 is on the graph. So you take a limit of this expression, and the first thing you do, you plug in. If you plug in 3, this becomes 9 minus 9. This becomes 3 minus 3, which is 0 over 0, which is indeterminate form and requires your algebraic techniques to finish the job. You notice 9 is the same as 3 squared. So a squared minus b squared is a minus b, a plus b. So we get the limit as x approaches 3 of x minus 3 times x plus 3 over x minus 3. These two cancel each other. And we get the limit of x plus 3 as x approaches 3, which is 6. So the limit does exist and it's equal to 6. However, h of 3 is 7, not equal to 6. Because the limit of h of x as x approaches 3 is 6, not equal to h of 3 equals 7, then no, h of x is discontinuous at x equals 3. In other words, this exists? Yes. This exists? Yes. Are they equal? No. That's how it fails. So what happens in part A, we plug in. We just plug in. Anybody has the answer for us? You plug in, this goes to 0. This is 3. 6 squared is 36, minus 7 times 6 is 4, minus 42, plus 12. The numerator remains at 3. The bottom is 6 equals 1/2. is a complex fraction. And if you plug in, because you get 0 over 0, you have to multiply by LCD, the top and the bottom, which is 3x. Since x is approaching 3, creating 0 in the denominator, we are hoping to get rid of x minus 3. We never distribute. We multiply these two, we get x. These two, we get minus 3. These two cancel each other. And now if we replace it, the limit becomes 1 over 9. At what point or points is f of x discontinuous? Name the discontinuity. If removable, how would you redefine to remove it? So first, quickly, we want to figure out where the function fails to be continuous. We start from the left and we go to the right. As we go from left to right, you'll notice at this point we have a hole, -2. At this point, we have a hole, -0.5. At this point, we have a jump. At this point, the same, so 0 and 1. At this point, 3, we have vertical asymptote. At this point, we have a hole. So -2, -0.5, 0, 1, 3, and 5. Those are the points we're going to discuss. We want to discuss them as to what type of discontinuity they are. So first, notice that 0 jumps from 3 to 5, and at 1 it jumps from 0 to 4. So 0 and 1 jump. Those are jump discontinuities. Also notice at number 3 we have infinite or VA, vertical asymptote. The rest of them, -2, -0.5, and 5 are all removable. So how do we redefine those? Well, starting with the first point, -2, notice if you come from the left and right of -2, from the left, we're moving this way. From the right, we're moving this way. Both of them are moving towards this hole. And that indicates that the limit of the function as x approaches -2 is 2. Therefore, if we redefine f of -2 to be 2, it removes the discontinuity and makes it continuous at x equals -2. The next number would be -0.5. -0.5 as we move from the left and right of that. Left takes us here, right takes us to the same point, and the same point has the y coordinate of 3.5. That makes the limit of the function f of x as x approaches -0.5 is 3.5. So if we define f of -0.5 as 3.5, removes the discontinuity as well. For the point negative 0.5. The last one is number 5. So what do we notice as we move towards 5 from the left? We are moving this way. From the right, we are moving this way. We are moving towards this hole, and this hole has a y-coordinate 5 that indicates the limit exists, and it's equal to 5. So the limit of the function f of x as x approaches 5 is 5. So if we redefine the functional value f of 5 to be 5, we remove the discontinuity and fix the formula.